Okay, look at that picture there. You see that's part of a topographical map. And let's zoom in here. And let's suppose that you are standing, let's say right here, at that point. Okay? If you wanted to stand there and face different directions, then you would see the ground around you doing different things. If you face one way, it might be going up. If you face another way, the ground might be sloping down. In some directions it's steep, and in some directions it's not very steep, right? All of those are derivatives. Derivatives show rate of change. Okay, and in fact, the partial derivative with respect to x would tell you the derivative in this direction. Okay, where I'm saying here, by the way, maybe I did not say this, so maybe I should. I'm talking about here where, well, that's really big. Hang on a second. Where f of x, y equals the altitude at the point x, y. Okay, then if you face, I don't want to do that. If you face east, which is the positive x direction, and you measure the slope of the ground in that direction, that slope would be the partial derivative of f with respect to x. If you were to face directly north and measure the slope in that direction, that would be the partial derivative of f with respect to y. But what if you wanted to measure the slope in some other direction? Let's say that. Okay. Let's say that that vector is a unit long, 1 unit long, and let's call it u. We're going to call that a directional vector, okay, because we're using it to point in a certain direction. Whenever we have directional vectors, we want to make them 1 unit long because the length doesn't matter to us, only the direction. And so we scale them so that they're 1 unit long, so that way the length is standardized. Okay, so here's the question. You're standing at that point, you're facing in the direction of u, and you want to measure the slope of the ground in that direction. That is called a directional derivative, okay, in the direction of u. Let me show you how to calculate that. First, I'm going to show you the definition, then I'm going to show you how to calculate it. Okay, so directional derivative of f of xy, let's say, okay, in the direction of the unit vector u. Okay, So I'm going to write for you the definition, but the definition is not what we use to calculate it, because there's a much easier way of calculating it. But first let's do the definition. Okay, the definition is, first of all, here's the symbol. We'll use a capital D subscript U f of xy. And here's the definition. It's the limit as h goes to 0. That should not surprise you because it's a derivative, so you should expect to see that limit as h goes to 0. Okay. Of what? F of x plus h times u1, comma, y plus h times u2 minus f of xy over h. What's u1 and u2? I should probably have written here. Those are the components of your direction vector. Okay, so that's the definition of the directional derivative of f in the direction of u. That's a definition. But here's how we actually calculate it. It is simply equal to the partial derivative of f with respect to x times u1 plus the partial derivative of f with respect to y times u2. This is a heck of a lot easier to calculate than trying to calculate this limit here. Okay? So that is the directional derivative of f in the direction of u. And you could very easily see that the partial derivative of f with respect to x is in fact the directional derivative of f in the direction of the positive x-axis, and the partial derivative of f with respect to y is the directional derivative of f in the direction of the positive y-axis. Okay? Now this is going to be a number, right? It'll give you some formula with x's and y's in it, and then you plug in the coordinates x and y depending upon what point you're at, and you'll get a number. Okay, that should make sense. Now, there's something else I want to introduce you to, which is called a gradient. Gradient of f. Okay, the symbol for that is an upside down isosceles triangle here. Some people write it as more of an equilateral triangle. That's fine, it doesn't matter. And a lot of times in books you'll see this top part and the side part be a little bit thicker. That is totally unimportant, don't worry about that. But that symbol though is not a Greek letter, it's a made-up symbol. I don't think it belongs to any actual alphabet, but we call it nabla. Okay, but in any event, that means gradient, and the gradient of f is a vector, first of all, and it is the vector whose components are the partial derivatives of f. The x component is the partial derivative of f with respect to x, and the y component is the partial derivative of f with respect to y. That's called the gradient of f. That's a vector. A lot of times, particularly in physics books, much more so than math books, you will see this thing called a gradient operator. And it'll look like this. So then when you see gradient of f, this is what they mean by that. It means you're applying this operator to the function f, and you get this. That's just the type of language and symbols that physicists often use. Okay? That's just for your own information. You don't have to worry about that for this class. All right, now, a couple of things I want to say about this. The reason why we're doing both of these together, directional derivatives and gradients, are because they're related to each other. I could right now, I could say, okay, we're done with the lecture. Now I'll go take some functions and calculate the directional derivatives and the gradients. It's very easy to do. It just means calculating some partial derivatives. Okay? But I want to say more. These things are related to each other. Let me point out how. I'm going to write relationship between directional derivatives and gradients. Here's the relationship. The directional derivative of f in the direction of the vector u is actually just equal to the dot product of the gradient of f with the vector u. Look up here and you'll see that. Here's the gradient of f. Okay? Write down for yourself the vector u. Oops, I wrote v and I mean u. And do the dot product of those two. And won't you end up with this? You do, don't you? So that's interesting. Okay, next thing. Let's zoom back into our picture here. I'm going to move that point a little bit. Let's put it right on one of these lines here. How about, I'll put it right here. Okay, let's call that point x naught, y naught. Okay, do you remember what these lines here are called that go around here? All of these. People who make maps call them contour lines. Mathematicians call them level curves. Okay? Now, let's zoom in a bit more even. I want to point out something to you. Remember, the gradient is a vector. And what I want to point out to you is that that vector is always orthogonal to the level curves, the level curve, I should say, not plural, the level curve that goes through a point. So here you can see, I'm going to try to make this level curve a bit darker here so we can see it. Let's see if I can get kind of a brown color. Well, let's see here. Not quite, so we'll just use purple. Okay, so we have this level curve going through here. That's too thick. Let me make it thinner. Okay, so we have this level curve right here going through that point. Okay, the gradient is a vector. The gradient will always be perpendicular, darn it, to the level curve. Okay, why is that? So let's make the gradient, how about we'll make it green, okay? Remember, gradient is a vector, okay? The gradient will always be orthogonal to the level curve and pointing uphill, by the way. And I'll tell you the reason why. I'm going to try to just write it right here on this map. Hopefully you'll be able to see what I'm writing here. There's a reason why. Because remember that the gradient of f at a certain point is equal to, what did we say it was equal to? It's okay, so here's what we're going to do here. Let's write u going in the direction of the level curve. Okay, so that thick purple vector is tangent to the purple contour line. Okay, the green vector is the gradient at that point. How come they would be perpendicular to each other? Well, here's the reason why. Remember that the directional derivative of f in the direction of u is equal to the dot product of the gradient with u. Now, what's the directional derivative of f in the direction of u? Let's think about that. U is tangent to the contour line. That means if you walked along the direction of u, you would be walking along the contour line, which means you would not be going up or down. Your height or your altitude would be staying the same if you walk in the direction of the purple vector u, which means the directional derivative would be 0, wouldn't it? So that means the dot product of the gradient and u is 0, and that means the gradient is orthogonal to u. Okay? So that's one interesting thing to remember. Okay? The gradient of f at x naught, y naught is always orthogonal to the level curve passing through the point x naught, y naught, f of x naught, y naught. In the picture, I just put two coordinates, x naught, y naught, and that's because we're just looking at a plane. But if this was actually 3 dimensions, then I would put f of x naught, y naught has the z coordinate. Okay? All right. Something else I want to go over. Let's zoom back in. Okay. Let's erase this stuff now. Let's go ahead and erase those vectors that we've drawn. But let me put the point back there. It doesn't have to be right on the level curve, so I'm going to put the point right here this time. Okay. All right, now, what if you were standing right there? Actually, that's not a good example. I'm sorry. I'm going to move it to, let's put our point, let's put it right here. Okay, what if you're standing right there? And you wanted to measure from here, from that point, which direction could I walk that would be the steepest upwards? Which direction could I walk that would be the steepest downwards? And how steep would they be? Okay, we're going to answer these 4 questions. F of xy equals sine of x cosine of y. And we're standing at the point where x is 1/3 pi and y is 1/3 pi. We have 4 questions. Number 1, find the direction and slope of maximum increase. Number 2, find the direction and slope of minimum increase, or if you prefer to call it, you could say maximum decrease. Find the direction or directions of no increase and decrease. And what is the slope in the direction of 2, 7? That should technically say, like the other 3, at P. Okay, so I know that I am going to need the partial derivative of f with respect to x and the partial derivative of f with respect to y. So let's go ahead and write these down. Okay, the partial with respect to x is cosine x, cosine y. The partial with respect to y is negative sine x, sine y. So at the point where x is pi over 3 and y is pi over 3, what do we have for the partials at that point? For the partial with respect to x, we have 1/2 times 1/2, which is 1/4. For the partial with respect to y, at that location, we have negative root 3 over 2 times positive root 3, no, yeah, that's right, sorry, over 2, which is negative 3/4. Okay, let's find the gradient of f at that location we actually already have it. Remember, that's a vector with this x component and this y component. So there's the gradient of f at that location. Okay, so I can already answer part of question 1. Find the direction of maximum increase. Okay, the direction of maximum increase is whichever direction the gradient is pointing. So that is essentially our answer. It's just that I want to make sure that I put my answer as a unit vector. Whenever you're using a vector to indicate a direction and nothing else, just a direction, then you should use a unit vector. Okay, so here's what I'm going to do. Let's rescale that vector to be 1 unit long. So I'm going to calculate the magnitude of that vector so that is the square root of 1/16 plus 9/16 which is root 10 over 4. Okay, so now let's rescale that vector to be a unit vector. How do you take a vector and rescale it to be a unit vector? You simply divide the vector by its own magnitude. And what do we get? We get the vector 1 over root 10 comma negative 3 over root 10. Okay, now we can answer questions 1 and 2. In fact, both of them right now. We have the answers already written down. Okay. Number 1. The direction of maximum increase. How about if we write it out as a sentence? The maximum increase at 1/3, 1/3 is, so first of all, how big is the maximum increase? We have that answer written right here. So the maximum increase is root 10 over 4. Let's put a comma, and let's answer the rest of that question. The direction of maximum increase. So, comma, in the direction of, and that answer is right here. The vector 1 over root 10 negative 3 over root 10. So there's the answer to question 1. Okay. Question 2. Simply change the signs on those things. The minimum increase or maximum decrease, whatever you want to call it, at that location is negative root 10 over 4, and it is in the direction of the vector negative 1 over root 10, 3 over root 10. That should make sense. If I'm facing the steepest ascent and I measure the slope of the steepest ascent, and then I want to know about the steepest descent, then all I have to do is simply turn around, right? And it'll be just as steep, except going down instead of up. Okay, now question 3. We are asked to find the direction or directions, there's going to be 2, of no increase decrease at P. What's that mean? If it's not going up or down, that means it's staying level, right? Okay, remember that the gradient is orthogonal to the level curve. So that means if we want to find the directions in which this surface is level, all we have to do is find the directions that are orthogonal to the gradient. And that's super easy. I'm going to show you a trick for that. Here's the gradient right there. You want to find something orthogonal to that. All you do is take the vector that we have here. There's the gradient. I want something that is orthogonal to that. All I do is switch the components and change the sign on one of them. So therefore, I could put here, so let's see here, the surface is level at P in the directions of, so remember what I said? We started with the gradient here, and I want something that is orthogonal to the gradient. So we swap the components and change the sign on one of them. So I can put 3/4, 1/4, and the other direction is negative 3/4, negative 1/4. But those aren't unit vectors, so let's go ahead and rescale them so that they are unit vectors. I already know the magnitude of those vectors is root 10 over 4, so I'm going to divide those numbers by root 10 over 4, and I'm going to end up with 3 over root 10, 1 over root 10. That's one direction in which the surface is level, and the other direction in which the surface is level will be negative 3 over root 10, negative 1 over root 10. all I did to explain this a different way, without using the word gradient, I'll explain my answers a different way. All I did was took the directions of maximum increase and I just wrote down the two unit vectors that are orthogonal to that. And you do that by swapping the components and changing the sign on one of them. Okay? Last question now. Number 4. What is the slope at P in the direction of 2, 7? Okay, so that means what is the directional derivative of F in the direction of 2, 7 at P? So it's the directional derivative of F in the direction of, now I'm not going to write 2, 7 down here because that's not a unit vector, is it? Let me ask you a question. How long is the vector 2, 7? I'm not writing it down, I know that, but I'm asking you to think about it. How long is that vector? Work that out for yourself. The vector 2, 7 has a magnitude of square root of 53, right? So for my direction vector, I'm going to put 2 over square root of 53 7 over square root 53. Okay. Okay, and this is at the point pi over 3, pi over 3. So do you remember that there is an easy way to calculate this? That is just the dot product of the gradient of F at that location with our direction vector. Sorry, my pen's not working very good right now. Now let me tell you something about this, how I rescaled this to be a unit long. This part over here, it would have been okay to just leave that as the vector 2, 7. I'm not going to call that wrong. But you can't put the vector 2, 7 here. You must rescale it to a unit vector in order to find the correct answer here. Okay, so that's important. All right, so what is that going to be? What's the gradient at pi over 3, pi over 3? We already found that up here. Okay, so we have 1/4, negative 3/4, and we want the dot product of that with our direction vector 2 over root 53, 7 over root 53. what is our answer going to be? 1/4 times 2 over root 53 will be 1 over 2 root 53. Actually, you know what? I'm not going to reduce that fraction. Let's leave it unreduced. I'm going to write 2 over 4 root 53. Okay, plus negative 3/4 times 7 over root 53. So that's going to be minus 21 over 4 root 53. Do you see why I didn't want to reduce the first fraction? I wanted to have the same denominator. So here's our answer. Negative 19 over 4 root 53. That is the slope in the direction of the vector 2, 7 when you're standing at the location of pi over 3, pi over 3. Okay, so this stuff is a new concepts, but the calculations are quite easy, I think. All right, that's all for today.